SwayamPrabha. Digital India. Educated India.
Welcome to the NPTEL online certification course on structural systems in architecture. So, today we will going to discuss the lecture number 7. This is in the module 2 in the strength of materials, and the topic of this lecture 7 is the theory of elasticity part 2. If you remember, in the part 1 we discussed the Hooke's law and the elasticity theory, and with that we also discussed the stress strain curve of a elastic material. So, this lecture we will have some of the further we will go with some of the other concept. We will start with the Poisson's ratio, then the shear and the rigidity modulus we will discuss, then we will discuss the bulk modulus, engineering properties of the material, that is already we have introduced in the last class, and then we also take you to further in that. We will discuss the concept of the factor of safety, and finally, the modular ratio. The learning objective of this lecture will be the some of the elastic concept we will define, and we will see what is how the application of the factor of safety works in the design principle, and we will also discuss the modular ratio and how it is associated with the structural design also. So, first let us discuss the very basics of the one of the elastic constant called Poisson's ratio. You see, when any axial force applied to a particular material, the material or a particular object, it will increase its length or maybe it is decrease its length because of either it is a tensile force or maybe it is a compressive force. Suppose it is a tensile force, and if it is a tensile force, if you apply the load in the two ends, definitely it will elongate from the original length, the final length, or in a particular stress, the length of the object will elongate. When it will going to elongate, the other direction, that is in the lateral direction, the diameter or the width or the breadth of the particular object will going to shrinken. So, it will be reverse in case of the compressive case. In compressive case, if you just put a compressive load, from the original length, the final length will be shortened, and with the same time the diameter will be elongate, or diameter will be increased, or the width will be increased. So, these two mutually perpendicular axes will behave in a different strain, I mean different type of strain. It may be the increment or the decrease in the original length also. From this point of view, this opposite kind of a strain in the right angle or the orthogonal the axis will take place, and this particular two type of strain in the orthogonal axis is captured in a ratio called the Poisson's ratio. It is defined as the lateral strain by the longitudinal strain. The lateral strain is the diameter direction, and the longitudinal stress will be in the strain will be in the length direction, and this two strain will be the ratio of these two strain will called as a Poisson's ratio. So, I have graphically tried to visualize the thing in this particular slide. It has a bar of this yellow color bar having a very thick bar having a diameter of d and the original length of L. And this bar after putting some load, that means that with some stress, if you put the diameter decreases by del d. So, it will be a bit thinner and the length is increased by del L. So, the longitudinal strain, longitudinal is the axis of the length axis. So, longitudinal strain will be the change in length by the change in the original length, that is del L by L, and whereas the lateral strain is in the diameter direction. So, change in width or diameter, that is del D, and then the original diameter is D. So, this divided by this, that is the lateral by the longitudinal, this 2, the strain, the ratio of these two strain will be called as the Poisson's ratio, and it is denoted in the with the mu, the Greek word mu. So, let us solve a small problem on that, and suppose there is a rod of original length 500 mm and it is elongated by 2.5 mm under a tensile load. So, as I know that the original length versus the this 0.25 is elongation. So, I can directly find out the longitudinal strain as 0.005, and it is also written in that during this process the diameter of the rod, which was actually 20 mm, the original diameter was 20 mm, was reduced by 0.05 mm. So, it is it should be clear in by virtue of your understanding or the practices that if the one is the increment, the other orthogonal directional, the strain will be the decrease, the opposite should be opposite in direction. So, by virtue of this data, we can say that the lateral strain which is in the diameter will be diameter direction will be 0.00125, that is much more smaller than the longitudinal strain, and now we can find out the ratio, and we can say that that material possesses a Poisson's ratio of 0.25. So, next let us discuss the shear stress and the shear stress and the rigidity modulus. Let us first define the shear stress. So, whatever we have discussed so far is the longitudinal or the axial stress when a particular body is under a load along its the axis, along its long or the length axis. But in case of the shear or shear force or the shear stress, shear force will give the produce the shear stress is it's actually it is all along with the axis, and when the particular perpendicular to the axis, it is not the along with the axis, it is the perpendicular or the transverse direction with the axis. So, what I have done over here, there are two green color plate, maybe a steel plate, it is lapping with each other, there is a common lap length, and these two plates are actually fixed by a rivet or maybe a nail or something like that, that is the riveting is done, and we are pulling from two sides, and if you pull with a heavy load, this rivet or this nail may break, and this two will going slice. So, if you see now in that portion of the nail or the rivet breaks, so this portion you see there is a slicing occur between the two part of the body, which was initially as integral part. So, there is this particular plane fails because of there is a shearing force. The shearing force applied perpendicular to the length axis of that, and it is a kind of a slicing force. So, we can say that this particular rivet or this nail is fails because there are two component equal and opposite of two stresses or maybe forces applied on a particular section in between these two the lap material, and it is going to fail. So, what we understand from here is that the shear stress is going to be a stress which will along with a plane of a body. So, it is a kind of a slicing kind of a thing, it is not a perpendicular to the body or so. So, suppose I have a block, metal block or any kind of a block, or you may say this is a block made by some the papers, or maybe you can imagine a book kind of a thing over here. And if I put a shear force, that is a tangential force on the top surfaces which is perpendicular to the one of the axis, so it will deform like that. So, if you have you can do it in a particular thick book, and if you just push from the top with your palm, then this book was now going to deformed. So, and what happened over here is that each layer of one material over the other will create a shear force transfer, and then this kind of a deformation will take place, and this deformation will take place from the original shape to a it will change to a deformed shape. So, this deformation whenever it is occurring, it is occurring due to the shear stress, it is not occurring due to the axial stress, that is the tensile or the compressive stress, it is occurring because of a tangential force or stress applied in the top of the body. So, it has some originality, and after the application of the load it is deformed to from its originality. So, if I can measure these two changes of the original to the deformed body. So, and if you measure the stress on this particular surface, we can find out some modulus of strain or modulus of this shear strain versus the shear stress. So, some shear modulus we can define. Now, the shear modulus can be defined as, so what I have drawn here is the one sided the sectional view of that particular block, which is having a height h, and under a shear stress of q, this is q is the shear stress which can be found out by Newton per millimeter. So, if you know the total surface area, if you know the amount of shear force has been provided on that surface area, you can find out the stress that the force versus the surface area, force by surface area. So, because of this application of the shear stress at the top, of course, there will be resultant shear stress will be applied in the base also, and because of that this red color dotted line is a deformed shape, which we have seen in the earlier slide, and because of this deformation we can measure the deformation by this angular displacement as phi, and this phi angle is so small that this tan phi tends to the phi, and so we can say that this phi can be written as the delta by h, where delta is a small increment of the lateral displacement at the topmost layer, and h is the thickness of the plate or the thickness of that particular block, which is actually practically it is tan phi equal to almost equal to tan phi. So, then we can write that tan phi is equal to tends to phi, it is if it is very small. So, the rigidity modulus or the shear modulus, which is expressed in G. If you remember, we express the Young modulus in E, capital E, and this is expressed in capital G as shear stress Q by phi. So, that way this has been developed, and this is another problem number 2, where we can have a small numerical problem to explain the shear stress and the rigidity modulus. So, a 2 meter by 2 meter metal plate is subjected to a shear force of huge shear force of 40,000 kilonewton. So, if it is so, so I can say that if 40,000 kilonewton is converted to Newton, and the 2 meter by 2 meter that is converted to the area in millimeter square, and I can find out that the shear stress, that is Q, this is your Q is your 100 Newton per mm square, and due to this load the lower surface of the metal plate is fixed, and the thickness of the plate is your 200 mm. So, the thickness of the plate, so the plate thickness, this h is equal to my 200 mm, and due to the application of the shear for the top face deformed by some very small amount, that is your almost that is your delta, which is your 0.24 mm. So, by these two I can find out what is the shear strain, that is going to be phi. So, this is the phi, and now we can actually make the ratio of the Q by phi, and we can find out that the rigidity modulus is this much. Another modulus, this is the third modulus after the Young modulus of elasticity, which is applicable for a linear stress or strain. Then the rigidity modulus, that is applicable for the shear strain, and the bulk modulus is a volumetric. So, something like a balloon, and you push or press it with some load or maybe some stress, and total volume of the balloon is decreasing, or you may from the internally you can increase the stress. So, the volume of the balloon is decreasing. So, it is how this volumetric the changes can be captured by some kind of a modulus, that is called the bulk modulus. The 3-dimensional body is subjected to perpendicular stresses in each of its direction, 3 dimension. So, suppose there is a block which is having a original volume V. Suppose you imagine that is I have drawn a cube most of the books drawn like a cube. Suppose you imagine it is kind of a balloon kind of a thing, which is having a volume, original volume V, and there are three mutually perpendicular directional stress of P, small p. So, suppose this balloon is underwater. So, if you just put the balloon is underwater due to the hydrostatic force, the each and every direction is under it will create a kind of a compressive force in the body of the balloon, and suppose that is B, and due to that particular force or stress of the hydrostatic or whatever, the changes volume is minor changes occur in this particular volume of the balloon. So, that is del V. So, the volumetric strain is nothing but this del V by V, and the direct stress is 0 going to P, and this the ratio of these two will be indicated or defined as the bulk modulus of elasticity, or it is given as the capital K. So, this is also one of the modulus, and these two modulus, or you can say it is the three moduluses are arranged, or they are interlinked with each other with two beautiful formula E and K, that is the E is your Young modulus and K is your bulk modulus. And if you remember this mu we have just now discussed, that is the Poisson's ratio, can be linked or can be associated with this equation, and this is E, this is Young modulus, and this is N, which is I have written here N, but this is also in the two earlier slide I have written as G, that is rigidity modulus. N and G, some books follow N, some books follow G. So, the N is the, now here I have written as a rigidity modulus, which is 1 my plus mu into 2 n equal to E. So, this way both of them can be thought of. So, if you know any two of the elastic property, and all are there are 4 elastic property altogether, E, K, mu and N or G. So, if you know any of the two, you can find out the third one, and if you know the third one, you can also go to the fourth one also. So, like that we can have the. So, that ends the elastic discussion on the elastic property. So, in this particular slide I have written down from the books some of the elastic properties of various materials, like the E values, the yield stress value and the ultimate stress value of aluminum, steel. So, steel is very important for us. The Young modulus of steel is 2 into 10 to the 5 Newton per mm, which is MPa, and your the yield stress is almost 250, and the ultimate stress fluctuate between 400 to 550, but this 250 is also I put a question mark, because there are various categories of steel. There are some high tensile steels are also available, which are more than 400, more than 500 also sometimes. So, depending upon the percentage of the carbon and how it is going to process, steel has various type of categories and various type of exhibit various type of properties. See, these are the some of the materials. Some of the materials like the brass, bronze, copper, rubber, diamond. Diamond is very high. You see, this is 10 almost. If it is steel is 2, diamond is almost 5 times higher. And you see the yield stress or yield strength 250, and it is 1600. Diamond is very high. Even our human hair is the elasticity is less, but you can compare the yield strength also. So, now let us discuss the next this thing as a factor of safety. The curve is very known to you. We have discussed that one. It is a stress strain curve of steel, and in the stress strain curve of steel there is a yield stress occurring at a certain distance after the proportionality limit. If you increase that particular stress, or if you increase the sample with a higher load, it will not going to increase the stress, but suddenly the strain will going to increase. Suddenly the strain is going to increase like this. Again it takes some stress and then go ultimate, and then go this is ultimate, and then it is going to rupture. But if I want to actually design for something, so for that the yield has been taken as the one of the criteria. So, we will load a particular the structural element such a way that this element should not have the stress beyond its yield stress. If it is more than yield stress, then the material will show plastic deformations and all, which will be not going to be suitable for a particular habitat areas, or the in case of any kind of the structural component in the habitat area. So, the yield is the ultimate. We cannot load a particular structural element such a way that the internal stress crosses the material yield stress also. But even yield stress is the ultimate or the maximum we can go, but still we should have a kind of a margin, safety margin. Suppose we will assume some kind of margin, and we go with some other, define that particular material with a particular limit of the stress such a way that is called as a permissible working stress, which is further less than the yield stress, and we will try to limit our the calculations, our design into this zone. So, we will do not try to cross this particular limit. So, suppose this is going to your 250, we may stick to 150 or something like that. So, even if it is 160, 170, it is still safe, still do not go for the plastic deformations also, but still we try to put ourselves within the 150 limit. Why? Because a kind of margin we want to put in between the safety and the working load also. So, even if a steel or maybe any material has its some yield stress, but the material we will have some kind of a permissible working stress which is much less than yield stress, and that will going to be our design will follow that one, that permissible the working stress in our design criteria. So, the ratio between the yield stress and the factor of safety is called the permissible. So, suppose yield stress is suppose something. So, we will divide that by a factor of safety which is definitely more than 1, such a way that your permissible working stress will be less than yield stress. So, from that point of view, let us discuss a problem and we will understand it better. The steel bar has to carry 80 kilonewton. So, it has to be carry 80 kilonewton. I understand that with some kind of the logic and some kind of the load mechanism that it should carry, it will going to carry 80 kilonewton. Still the yield stress of the steel is found as 250. Okay, fine. And then the using the factor of safety of 1.25, estimate the diameter of the this bar is required. So, what I can do is that I know this is the yield is 250, and as I know this is my factor of safety is 1.25, my permissible working stress will be 250 by 1.25, that is your 200 Newton per mm square. So, I will not going to allow this particular body or particular structural object to cross that 200 Newton per mm square stress, that is the permissible, that is the maximum, working. So, if I know that there is a expected loading is 80, so I can find out the required cross section area by the load by this permissible. So, 80 into 10 to the power 3 Newton by 200. So, I know that my area should be 400 mm square, because that 400 mm square can take 80 kilonewton load with a stress limit of 200 Newton per mm square. So, if I know the area is 400, I can easily find out the diameter as 22.56. So, this way the design will be occur. So, always we will take care of the permissible working stress for our any design criteria to develop the what will be the diameter, what will be the length, what will be the cross sectional area and other things. So, next one is the percentage of elongation. Suppose as you understand that under a tensile stress this particular bar will going to increase. So, at initial stage this bar the length is L naught, and in the at rupture it is LF. So, there is a percentage elongation we can find out from the LF minus L naught by L naught into 100. So, how much percentage elongate by the virtue of the loading. This is be very much useful in case of the if you want to check the ductility of the material. So, there are different type of failure will occur in case of that rupture, and one of the ductile failure is called as the cup and cone failure. This is pure ductile failure where there is a two kind of a cup is formed, but steel will fail like that, but brittle materials like piece of chalk or concrete will going to fail like a slicing kind of a failure, that is called the brittle failure. So, we have another problem on that. So, I have the some data. So, a gauge length, that is the length of the particular sample, was 600 mm and diameter was 16 millimeter. It is tested on a particular load test, and the failure length was, at time of failure, it is 675, and the maximum load recorded in the test, not at the failure, but in the test, is 95.5 kilonewton. So, you have to find out the ultimate strength and the percentage elongation. So, I have found out the ultimate strength as this 95.5 is the maximum load by 201 is the cross section area of the test sample, and also I have found out the percentage elongation as 12.5% or so. Let us finally go to the modular ratio, the concept of modular ratio. There are two bar, A and B and this bar are having different length, L A and L B, different cross section area, and as it is two are of different material, are having two various values of elasticity E A and E B, and it has under a loading cap. And if I put a P load on the loading cap, the share of A is suppose P A, and the share of load the bar B is suppose the P B, and then these two are the stress also we can find out as a P A by A A and P B by A B as a stress at A and stress at B. Now, I can also find out what will be the elongation in the bar A by virtue of the Hooke's law. So, this is the elongation of the bar A, and also similarly this is the elongation of the bar B. So, everything will be under the suffix with A and B in the bar for the bar A and bar B. Now, there is a compatibility equation. These two elongations will be equal. These two elongations will be equal. Otherwise, this two bar will not going to act as a purely the monolithic way or the homogeneous way when there are two this composite sections are there. And for this two bar, when this is both are this thing, both the elongations are same. Please note that the strain are not same. The compatibility equations, that is the elongations are same. Then only the loading cap will be moved down in a similar order. So, by virtue of this compatibility equation, I am equating this and this two, and finally, I can find out the what is the ratio of their stresses sigma A and the sigma B. Sigma A and the sigma B is written as the E A by E B, that is the ratio of their Young modulus and the inverse of the ratio of their length. So, if so this M is the modular ratio, the ratio of their Young modulus. So, theoretically the modulus of modular ratio is the ratio of the Young modulus, the modulus of elasticity of two material, and it is actually expressed as a stronger elasticity of the stronger material by the elasticity of the relatively weaker material in a composite beam or composite structure, right. And now, if I know these two stresses, I can easily find out what is the shear. So, this will be the equation, because the total load P equal to P A plus P B, and P A is sigma A by the area of A and sigma B by area of B. This is the final governing equation to find out the shear of load or of these two particular materials. So, we can easily rewrite this as in this case, if I say that if the lengths are same, in that example I have shown that both lengths are the lengths are not same, they are not equal. So, if the length are same, this is going to be equal to 1. So, the sigma A by sigma B, the ratio of their stresses will be equal to the modular ratio, and we can use this first equation, and from the first equation we can replace the sigma A equal to m sigma B, and we can find out the sigma B, or we can also replace the sigma B as sigma A by m, just reverse, and we can replace in this equation and then finally find out the sigma A also. So, either of these two ways you can have two paths, you can find out the sigma A and sigma B, and that can of course require the modular ratio and the A values, the cross section area values. Please remember, this is for the when the lengths are the same. So, I have one problem, it is a column which is having a gross cross section area of 300 by 300. So, it has 4 diameter, 4 reinforcement also, 4 bars also, 6 mm bar, and it has applied a load of 2500 kilonewton, and modulus of elasticity of steel and concretes are also given. So, you know the area of steel, you know the total area of concrete, you know the total load, and you also know the modular ratio or the both the E values. So, I have to find out the what is the total share of the stress and the total share of the load due to this particular application. So, I have found out that the steel total reinforcement area of the steel is 804, and gross area of column is this. So, I can take out that 804 from 90,000 or 900 yes 90,000 to find out the area of concrete also. So, I know that this too. So, I know that this is the modular ratio is 11.5, the strong material versus the weak material, and as both are having same length, the sigma s, the stress of steel is equal to 11.7 times stress of concrete. Now, I can use this first formula that the total load is the stress of steel multiplied by the stress of concrete, sorry, area of steel plus the stress of in concrete into the area of concrete. So, I can use that, and finally, I can find out the replacing all the values. This is 804 is the area of steel, and this is the area of concrete, and 11.7 sigma c is the proportionate stress in steel, and sigma c is the stress in concrete. So, finally, I can find out the how much is the stress in concrete, and 11 times will be the stress in steel, because the modular ratio is 11.7. So, stress in steel is almost about 300 and stress in concrete is 25, it will around 25, and from that if you multiply with the area with that stress component. So, I can find out the concrete will take almost 2256 kilonewton load, and the share of steel load is 283. So, and if you add, it will be almost close to 2500. So, I took this reference for this particular chapter. So, in finally, I conclude with the elastic properties, which is very important in our studies of the structural engineering, has various parameters like modular of rigidity, Poisson's ratio, bulk modulus. They are related with the Young modulus, and modular ratio is one of the prime factor governing the designs and all. So, we will take that modular ratio in the further to go ahead with the some of the further design principles. So, I have two homework for you. This first problem, I have given a tensile test load data, tensile load and the elongation of a body. You have to find out these particular values, modulus of elasticity, yield stress. You have to plot it, or sometimes from this data also you can find out that what could be the answer. The second one I have done for a exercise for the modular ratio. So, just like our first example, I have given 2 bar with a loading cap, it is 50 kilonewton load on a red material and the blue material, you can say, two various posts under this load. We have to find out the what is the will be the stress in the various red and this post. I think thank you very much.